director of similar consortium. As you know, we have Nuclear Science and Security Consortium here at Berkeley. It was awarded a few years ago in 2011 by NNSA 922, and Sara Pozzi and her large group that she will talk about today got a similar award last year. So we'll hear about what are their plans. I know Sara for many years, and we tried to recruit her to come here to Berkeley. We were unsuccessful, and I'm still, upset about that. So anyway, let me just tell about her background. So she earned her master and PhD in nuclear engineering at Polytechnic of Milan in Italy in 1997 and 2001. And her research interests include the development of new methods for nuclear materials detection, identification, and characterization for nuclear nonproliferation, nuclear material control and accountability, nuclear safeguards, and national security program. So there are a lot of things that overlap with what we do. But what is also interesting that she is a co-author of the Monte Carlo code called MCMPX Polini that we also, I believe, have and used. So it's excellent code. And it's being used at over 50 institutions worldwide. She also has a huge list of papers, over 300 or so, in journals and in conference proceedings, and gave a large number of seminars, as she will do right now. And currently she advises 14 doctoral students and many undergraduate students. Welcome.
Thank you, Professor Bujic. It's a pleasure to be here today. I'm very excited. And not only because Michigan just had a huge snowstorm, there were 18 inches of snow, so thanks for getting me out of there just in time to be here in this wonderful weather. I don't see how anybody gets anything done here. I would just be outside and running on the trails. Well, Jasmina, thank you so much for this invitation. Your consortium has been greatly successful. For this reason, NE22 has decided to award 2 more of these consortia. And I have the honor of leading one of them, the Consortium for Verification Technology.
I must add female power.
Well, we just got this awarded, so it's a 5-year grant, $25 million, similarly to your consortium. And we are tremendously excited about the possibilities of working with our partner institutions and with our sister consortia here. And today we've made a lot of plans for collaborations and student exchange and so on. So with that, let me tell you a little bit about the overview of the mission of our consortium. So since the first consortium was awarded, I think NNSA got a little bit more specific into what they wanted out of these consortium. So our consortium has a very clear mission, and it has to do with verifying nuclear weapons treaties. And I'll tell you a little bit about what we mean by that. So, as you know, in the 50s and 60s, after the war ended, there was a race to produce more and more nuclear weapons and separate more plutonium and enrich more uranium at the point that we have so much of this special nuclear material around the world. And so we are really looking at controlling that material, verifying it, safeguarding it, and these are topics that are also of interest here, I know. And so with that fast-growing expansion of these nuclear capabilities came some nuclear treaties that were set into place to try to counter that. So the most notable is the Nuclear Nonproliferation Treaty that came into force in 1970 and put nuclear safeguards as a safeguards regime to control the nuclear material in various facilities. However, we know that there are states, both inside and outside of this treaty, that are pursuing elements of nuclear weapons program. There are other treaties that have been negotiated to limit and to stop the testing of nuclear weapons and reducing the arsenals of the Soviet Union and the United States and other states. So the overarching mission of our consortium is to advance the state of the art in technologies, primarily technologies, but also, as you will hear, a policy aspect related to verification of these nuclear treaties. So what do we mean? Which treaties are we most concerned with? Well, I mentioned the NPT, Nonproliferation Treaty, that is verified by using safeguards. So we worry about new safeguards techniques. The additional protocol, which is a secondary treaty that was tagged on to the NPT that would allow additional inspections into the states. The fissile material cutoff treaty, which is under negotiations, that says, well, we shouldn't be separating any more plutonium. We shouldn't be producing any more highly enriched uranium. We already have so much of it. So let's have a cutoff on this fissile material. And here we talk about plutonium and HEU as special nuclear material. That is as defined by the IAEA, and basically it's the primary component of a nuclear weapon. It's what makes the weapon work. And then we also look at the comprehensive test ban treaty that has been under negotiation for a long time, which would ban any nuclear explosion for any reason at any yield. Okay, so that's in contrast with a limited test ban treaty. The comprehensive test ban treaty goes down to say no nuclear explosions for any reason. And so this has been under negotiation, and one could argue that the reason why we don't have a treaty yet is that we don't have a good means to verify that states don't actually break that treaty. So how do we verify that there are no nuclear explosions in a given state? So we'll talk about that a little bit. And also disarmament treaties. So we have some powers that now have hundreds, thousands of warheads, and we'd like them to disarm. Well, we want to verify that this is actually happening. And do we have a way to verify that by means of measurements of that warhead without giving off the information on how that warhead is made? Because that is obviously classified information that the states don't want to give out, right? So our consortium is focused with 6 thrust areas. And the first thrust area is actually policy thrust that our friends at Princeton are leading. And here, what we are looking to happen is that the technology that is developed in the other thrust areas be informed by knowledge of the policy. So that's why we have this thrust that kind of overarching over all the other thrusts. And then we have a thrust number 2, which talks about fundamental data analysis techniques and some fundamental physics studies that are cross-cutting and then cut across all the other thrust areas. And we have a thrust on advanced safeguards tools, looking to develop the next generation of instruments for safeguards applications. And then a thrust on undeclared activities. So when we read in the newspaper that North Korea has had a nuclear weapons test, how do we detect that in a way that allows us to make that claim that that in fact was a nuclear weapon and not, say, an earthquake? Okay, so we have thrust on that. And then thrust 5 is in disarmament verification. And all of these thrusts feed into the education and outreach which here at Berkeley is being done so well. So how do we take the next generation of students and give them the tools they need to address some of these really important technical questions? So educating the next generation of professionals in the areas of nuclear nonproliferation and safeguards. So all of the institutions are working on that. So of course, we needed an org chart because this is a big consortium. So up here we have our sponsors, as you heard, NNSA, NE22 is funding this consortium. I serve as the director. Chief scientist is Professor David Weehee at the University of Michigan. My assistant director, Dr. Sean Clark, again at Michigan, and we now have a project manager, which is great, John Rodriguez. And then we have an advisory board that we are working on. We have initial composition, but we are looking to add a few more people to that board. And here we have each of the thrust areas shown here in green. Each of the thrusts are led by a thrust area lead. And as you can see here, we have Michigan leading thrust 2, Al Hero, Zhang He of Michigan thrusting, leading area 3, and then we have Columbia, Paul Richards leading area 4, Dick Lanza from MIT area 5, and Alex Glazer from Princeton on area 1. And finally on thrust area 6, Professor Kim Kierkegaard at Michigan. So as you can see, the consortium is very exciting in terms of the number and the quality of the institutions that are involved. So we have some institutions that are, let's say, major participants with larger projects, and those include MIT, Columbia, Princeton, NC State, and then we have Hawaii. Then we have some institutions that we selected because they brought a specific capability. So they are funded, let's say, at the one project level. And so those include Illinois, Penn State, Wisconsin, Yale, University of Florida, Duke University. So I think I mentioned them all, but you can see them here on this map. And as well as the university partners, we work closely with the national laboratories. The national laboratories are not funded directly by us, but they provide that mentorship to our students, which is very important for their education. So we have actually 9 national laboratories involved in the consortium, including Lawrence Livermore and Lawrence Berkeley, where I'll be tomorrow. So I'm very excited to be able to spend the day tomorrow with our national lab collaborators there up the hill. So that is a map showing the consortium partners. And now I want to tell you just a little bit about each of the thrust areas and some of the projects that are going on in these various thrust areas. So here in thrust 1, this is our policy thrust, where we look at any existing gaps that may be in these policies and any emerging challenges. And we're focusing on a fissile material cutoff treaty, which would prevent the production of new plutonium and new highly enriched uranium for weapons use. And this potential treaty, not existing yet, has a lot of verification challenges. Some of them are already included in our safeguards, traditional safeguards regime. Some of them are specific to what is being sought after in this treaty. So our Princeton colleagues are working on studying that, as well as future disarmament treaties. So on Thrust 2, this is our fundamental data and techniques. We work on the physics of fission. One would think that by now everything is known about fission, as we've discovered this reaction several decades ago, but we are still missing some information about it. We know a lot about the average values in fission, let's say like the average number of neutrons or gammas, but we really don't know much about correlations between them. And so we are very interested in studying what happens in fissions, what are the correlations that exist in fission, and specifically experiments to do that. Under this thrust, we're also working on data analytics. As I will tell you a little bit later, we have measurement modalities that vary in this consortium by a lot. So we have partners who are working on detecting, let's say, seismic signatures, infrasound signatures, radiation detection signatures, so very diverse. So how can we use those signatures together to give us a more robust answer as to, for example, has an event occurred, where has it occurred, and so on. So this is where our data analytics team comes in and really takes that data and is able to merge it and come up with interpretation of the data. Radiation detector systems are used in many of the projects, and one of the challenges we have is data acquisition systems. Now we can digitize all of our signals, and we have many detectors. We have a huge data rate that's coming in, and so there's a need here to really perform data acquisition at a level where we can have multiple detectors, maybe for imaging or for other applications, and we can read out all these signals at the rate that we need to. So we have a project going on looking at that and even putting some of the algorithms that we developed directly on the FPGAs that read out these detectors to make the process much faster in real time, which is very important. So I want to say a few words about our physics of fission experiments. This is a project that my group is working on. So this is an induced fission experiment where we're looking at induced fission on uranium-235. And we're doing this with our collaborators at Los Alamos. So at Los Alamos, we're using a Lawrence Livermore designed U-235 fission chamber. So in this chamber, there's 10 plates. Each of them is plated with U-235. And we place that chamber in the beam. You can see the chambers right here. And the neutron beam comes through this in this direction. Basically, these neutrons come from a spallation source. It's a high energy, 800 MeV spallation source. But we have time of flight. So we have time of flight both from the spallation to the chamber, and also from the chamber to these detection systems that we developed in my group. So it's a double time of flight experiment that allows us to detect neutrons and gamma rays in coincidence from fission events. And so we've done some measurements up there for a couple of weeks at the WNR facility, and we observed about 2.6 times 10 to the 7th fissions. So it's a pretty slow process, okay? You have to be very patient. You only get a few fissions per second. So what we observed is we could measure the angular distribution of neutrons. And we plot those as a function of the angle between the neutrons. So we can see that there is a strong dependence on angle of the emission of neutrons from fission. And so this was an interesting result. We did experiments in 2012 and 2013, and we were very happy that the data actually agreed from those two campaigns. And we also plot that data with the Californium data. So Californium is a spontaneous fission isotope that also fissions, but of course the fission is very different. But what's interesting here is that the data falls right on top of the other data. So showing that there's really some inherent physics in the fission process that is reproducible, and that you can see here. So we also look at the average detected energy for pairs of neutrons as a function of angle. Because we know the energy because, again, by time of flight, we have an approximation of the neutron energy to our detector. And again, we see some strong angular correlation between the energy of emission and the angle. And this goes back to the fact that in binary fission you have two fragments, and when the neutrons are emitted back to back, they get a boost from the fission fragments. That's why you see this increase here at 180. You see an increase in the average energy detected. So this research is experimental, but we do compare our experimental results with results from theory, including from our collaborators at Livermore and at LBNL, particularly in the Freya code. So we also have a project looking at fast neutron emission. This is a very fascinating detection system that looks at the direction of arrival of neutrons. This was developed at Sandia Livermore. And in its original implementation, there were multiple simulator cells arranged in two planes. And by observing two neutron scatters, we were able to determine a cone of possible locations of the neutron source. So this can be used to image a fast neutron source, such as a fission source. So it's really interesting for nonproliferation applications. So the idea here is to go from this approach where you had multiple cells and multiple planes into a single volume approach, where we're able to read out a single volume and to resolve the individual neutron collisions within a single volume of, say, simulators. So if we could do that, if we could read this cell out by using a pixelated photodetector, we'd be able to, again, see where those interactions occur and determine the position of the neutron source. This leads to improved efficiency when compared to this approach, perhaps at the expense of huge complexity, right? Because this is quite complex. Quite complex endeavor to be able to do that. Alternatively, what one could do is you could take that single volume cell and optically decouple it, say in multiple pillars of simulator or something like that, that would be optically decoupled. So we're looking at all these various options for a fast neutron imager. Okay, so I'm going to say a few words about our advanced safeguards tools, this time for accessible facilities. So what we're looking at here is verification of facilities under safeguards. And here we look at neutron multiplicity counting and a new approach for that. As you know, neutron multiplicity counting has been around for a long time based on helium-3 detectors. Those helium-3 detectors are right now in short supply due to the limited amount of helium-3. And so we're looking at a new concept that involves the use of organic simulators, whether they be liquid or still beam-based simulators, to do multiplicity counting. We're also looking at a handheld, portable, room temperature counter gamma ray imager based on CZT detectors, which has been a strength at Michigan over the years. Standoff measurements using libs provided by Penn State, and concept for chain of custody detectors. This is where you have, let's say, weapons in a facility, and you want to make sure that you don't lose chain of custody of those weapons once you have them in a facility. So I'm going to say a few more words about two of those projects. So in this one here, my group is developing this counter, which will include both liquid simulators and still beam detectors, and I'll be talking more in detail about those simulators tomorrow. But there's been a lot of development in still beam right here at Livermore. New techniques for growing the crystals into larger shapes, more reproducible techniques so that we can grow them faster and better. We use pulse shape discrimination to be able to identify each pulse on a pulse by pulse basis as a neutron or a photon. And by using this technique, we can actually look at multiples within a given time window. And so in contrast to helium-3 type counters, there's no thermalization time here. So our time windows are, say, 40, 60 nanoseconds versus 60 or 100 microseconds. So here we're really gaining, by shortening that window, we're gaining a lot in terms of our accidental coincidences by orders of magnitude. So here you see some preliminary proof of concept experiment. So if we put a source right here in the middle of this assembly of detectors, we do that with a plutonium beryllium source and with a californium source. So obviously this source is an alpha N source. So each time you have an event, it's a single neutron, sometimes with a gamma ray. So the singles to doubles rate is very different when we look at an alpha N source versus a spontaneous fission source, where the singles to double neutron rate is much different. And this has to do with the emission of neutrons from fission. So a lot can be done to characterize materials and evaluate, how much mass is in a given sample, which is one of the safeguards. Quantities of interest is determining what's the mass of plutonium in a sample. And these are some experiments that we performed at the JRC in ISPRA, where you see kind of a doubles rate as a function of mass. So what you have here on the x-axis is the mass of plutonium-240 effective, and on the y-axis the number of doubles per second that were measured. You can see there's a pretty linear trend here. As you can see, we have a lot of data points down here and just a couple up here in the 50 to 60 gram range. So that's just due to the fact that we didn't have the whole set available for these measurements. So we plan to really fill in this gap in our new experiments. And we're going to do these experiments at Idaho National Lab, at the Zipper facility with our collaborator there, David Chichester, who has some plates of plutonium that we can use and really go up in mass up to several hundreds of grams of plutonium. And we will bring our prototype system there. So a few words on the Polaris system, which is being developed at Michigan in the last few years. We're very proud of this system. It's really exciting how it's being developed in the R&D phase and then transition into a startup company, H3D, which is now commercializing this technology. And here you see an example of one of these systems. And typical resolution for these types of systems when compared with HPGE and sodium iodide. And what you can see here is that we get really good energy resolution, but still being at room temperature. which is a big advantage in our field operation. What you can see here is Professor Zampi is in this picture and his students. And some of the students are holding a radiation source. Mind you, it's a very weak source, so it's all safe. They're holding it and showing how the system can actually pick out these emission lines. So we're able to characterize the source. And in addition, we're able to show you a hot spot of where that source is located. So energy discrimination and location of source, which, as you can imagine, is very important for safeguards of facilities, measurements like hold-up measurements, where you're trying to find uranium nuggets. There's hold-up in pipes in a facility, and being able to image that facility with this type of energy resolution is very important. Okay, so thrust 4, undeclared activities. So unfortunately, sometimes we have states, parties, who are actually developing undeclared nuclear weapons program, and in some cases, even to the point of being able to test some of these weapons. We've had 3 tests from North Korea in the last few years. And so we have these signatures that can be used to detect this type of event. And we have a network of detectors around the world that are used to detect these types of signatures. So I'm going to just show a really brief video. It's only about 1 minute long, showing you the network that we have present around the world to detect these types of events.
The CTBTO Global Alarm System spans the entire globe. Its 337 monitoring facilities are located in 89 countries on all continents and cover all oceans. The system also features an international data center in Vienna and a global satellite communications network for data transmission. When an event occurs, several stations may detect and register the event. Data containing information such as location, time, and magnitude of the event are recorded. Data are transmitted via the global satellite communications network, which is comprised of 5 satellites positioned around the globe at a height of approximately 36,000 kilometers. The satellites route the data to hubs on the ground. From there, data are transmitted through protected connections to Vienna. The entire data transmission from a monitoring station to the International Data Center in Vienna takes place in a matter of seconds. At headquarters in Vienna, scientists process and analyze the data in several steps. The raw data and the analysis results are then distributed electronically to member states all around the world.
Alright, so that gives an idea of what is already in place and the type of data that can be acquired. And we will be using some of this data in our consortium. So we'll have the actual measured data, and we'll be able to test the new algorithms that we will develop on this real-world data. So our friends at Columbia University work on analyzing the seismic signatures from events. And first of all, they work on detection. That is, answering the question about whether or not a station actually had an event occur. And then associate different signals from different stations that might be around the point of interest to determine if all the different signals were from the same event. It's really important to determine where the event happened so that we can have attribution to a particular state for an event. Identification is a really important part of it. So we want to be able to distinguish earthquakes or other events from a nuclear explosion. So it's really important to be able to do that. If it was a nuclear test, then what country conducted it? So again, really important to have location. And then an estimate of the yield is also extremely important. And that goes together with location. So along with the geographic location, how deep was it? Was it a really deep event or was it more of a surface event? So all of these questions will need to be addressed and answered by our collaboration. As well as the seismic, we also look at infrasound, and here you have an example infrasound map. So infrasound are really slow waves that travel really far, and they can be picked up by these various monitoring stations. And our collaborators at the University of Hawaii are developing new systems, including systems to place infrasound detectors in a more ubiquitous way, for example, inside our iPhones, so that we could have a ubiquitous network of infrasound for these types of events.
What's the typical frequencies that they're looking for infrasound?
Those are big,
Very-
like hundreds of meters
Yeah.
times scale of the wavelength. This is the radio xenon release, so this is the third detection that we're looking for. So looking at these xenon isotopes as produced in nuclear explosions. So if the explosion is underground and it bears venting, that means that there's release to the atmosphere of some of these, then we can detect them. Most of these are short-lived and will decay shortly after production into other elements, but these, you see, have half-lives of the order of days, and so they can actually be very useful for verification. And here we're coming up with new detector systems based on beta-gamma coincidences to detect these that would be then deployed at some of these stations that I showed you earlier, so that we could have this detection of radioisotopes. So this is the final technical thrust area. This is the disarmament verification. And here, led by MIT, we are looking for ways in which we can come up with a verification system that both parties can agree to. So when we decide that we're going to dismantle a certain number of weapons, we can agree to a system of verification that doesn't provide any classified information to the other party. So these are some of the approaches that you see here. In the zero knowledge approach, we have some non-electronic detectors, which means that you just load them up and you place them, and there's a readout afterwards. So there's no electronics needed in the actual measurement. And you would have these detectors here and a reference object as well as a test object. And then by irradiating, it's an active interrogation technique. So you have DT generator that would irradiate the system, and then what you would do is compare the response of those two events. And that way, you'd have a high confidence that this is actually a warhead and not something else, right? That's being dismantled. So this could be done by letting the host preload your detector, then having several of these available, and then at that point, the inspector would select which preload goes with an object, and that would give you an increased confidence that what's happening is actually a true dismantlement of a weapon. Folks at MIT are working on an NRF approach. This is not the traditional NRF, but it's an NRF by means of a witness foil. So the way it works is you have a beam of photons, typically you use a Brenner beam, and this beam goes through the object that you're interrogating, and you don't measure the lines directly from the object because that would reveal way too much information, right? You have isotope-specific information on your object and you don't want that. So what you do is you place a witness foil, and basically what comes into your foil is the transmitted spectrum minus these notches, which correspond to your absorption of NRF absorption lines. So you hit your foil, and at that point, if the two objects are the same, that is, if this isotope is present in your test object, then what you have here is reduced emission lines over here in your backscatter detector. On the other hand, if the two are different, then you would still get those emission lines. So you'd be able to see if your object contains what's in your witness foil. And so some part of this approach could be used in a zero-knowledge verification scenario. And this is something that MIT is working on. All right, so I'm going to finish here with the last thrust area, which is thrust 6. Talks about education and outreach, and everybody in the consortium is very interested in this area and contributing to this area. We are establishing CBT research fellowships. These are extremely important fellowships that fund both undergraduate, graduate, postdoctoral fellowships at our partner institutions. We also would like to fund faculty sabbatical fellowships and national lab expert fellowships so that national lab collaborators could spend some time at the universities to share their knowledge there. We focus a lot on career development of our student fellows, so we have programs to do that and to transition them to the labs, which is very important for our sponsors. When they talk to us, they talk a lot about the national labs and how those collaborations are going. We're going to have new and enhanced academic courses that students can take. So not only students that are directly funded by the consortium, but also other students that learn about these topics. And public policy, I mentioned that. We have Ford School of Public Policy at Michigan, and other institutions have other public policy schools. So the students are encouraged to take these certificates in addition to their education and study engineering or science or physics. Outreach, well, we have a yearly workshop that Jasmina has been to this past year. Conferences, summer schools, inclusion of underrepresented minority schools in our consortium, as well as INMM student chapters. We have 3 very active chapters in our consortium, so we work a lot with them to send students to the INMM meeting. And this is a really good meeting for seeing both the technical, but also a lot of policy talks. And the students have really enjoyed that meeting. It happens every year in July to learn a lot about these topics. So we have upcoming experiments at the DAC facility in July. Here we're going to be able to measure some weapons grade material. So we're very excited about that. We have access to the burp ball, which is a 4.5 kilogram unclassified object. and it's weapons-grade plutonium, as well as rocky flat shells, HEU nesting shells that we will be able to measure as well. We're deploying 3 imaging systems in this experimental campaign. Polaris that I talked about, dual particle imager, and a jointly developed coded aperture neutron imager. So what we'll be able to do is take the object, place it in the middle of the room, and then deploy 3 different imagers around the object at the same time and compare these experiments. So this is our dual particle imaging that's being developed in the group. What this consists of is a combination of a Compton imager and a neutron scatter camera in the same instrument. So the first plane of detectors are liquid organic accelerators, and the second plane is a checkerboard configuration of liquid and sodium iodide. And so by reconstructing cones of coincident detection of gammas and neutrons, we can come up with images, both neutron and gamma ray images of an object. And what you see here is a measurement of 2 MOX canisters that emit neutrons and gamma rays, both. So you can clearly distinguish 2 different hotspots in these images, and it's kind of a proof of principle that it actually works. And we think it will be very useful for detecting shielded special nuclear material. When one of the 2 emissions is shielded, we still have sensitivity to the other one, and so on. So this is my final slide. So this is showing you some of the deliverables and outcomes over the next 5 years that we are going to look at the policy, but also technical aspects of nuclear treaty verification, and coming up with the next generation set of computational capabilities for the data analysis and data fusion of multimodal detection. And this will lead to an improved detection of these what's called anomaly scenarios. So can we really detect a nuclear event? Useful in nonproliferation and safeguards applications. Capabilities and tools for the declared facilities, as well as undeclared activities and facilities, and disarmament verification. And finally, very important, over 60, that number is kind of low because we're already above that in terms of recruitment. But at the time of our proposal writing, we said more than 50 graduates with talent, training, and commitment in these fields. Okay, so that's all I have prepared for you, and I'd be happy to answer any questions. Excellent talk, so thank you. Questions? Okay.
You're trying to determine about the same thing with like multiple technologies. I come from the oil industry. One of the things we've struggled in the depth of investigation of different technologies, they vary. How do you put that in here?
Yeah, that's an excellent question. So the diversity and also the different technology readiness level of many of the things that I showed you. So some of these things are just at the idea level. Let's see if it works. Some of these things have already been developed in the R&D space, maybe even tested, maybe even commercialized. And so this will be one of the challenges, is to really see how do these technologies play together and how can we really get more than the individual parts. So putting together all the parts, but having an outcome that is more than the sum of the individual parts. So that's an excellent question, and the way we do it is by constant, frequent education, like we're educating each other on the different topics and technologies. We're learning a lot. Of course, we're just starting, but yeah, we're planning on doing more and more in this interaction.
So I noticed that you were talking about commercialization of Nuclear Technologies with H3B. Is this an official connection to the consortium, or are there industry partners as well as academic partners?
Right, that's a great question. So we don't have industry partners per se in the consortium because the funding and the idea here was to really fund university academic research, not so much industry. However, in this case, we have the inventor of the camera in our academic partners. So we clearly have that strong connection with this particular industry partner.
If I remember correctly, John mentioned when I was last time there that he was forced to commercialize because there was a gap in funding at that moment. So in order to continue funding his group, he tried to commercialize, and it worked. So it's really great.
And he's hired, 4 or 5 of his former students from his group into this startup.
Yeah, very good.
Yeah, related to that, any commercialization of the equipment that you develop would be on the side, because I think you are using your equipment to detect weapons material. So IAEA is really the only customer. Do you see your technology will migrate into use by IAEA, or actually in some case between countries that have disarmament verification,
Yes.
like US and Russia? But in that case, most of the things are being done a bit separately than what you are talking about. Am I right?
Right. That's a great point. I mean, the IAEA is an obvious customer for what concerns safeguards applications. So they're looking for new and better detectors to do that job, right? To have inspectors go around with detectors. And, that would be one obvious, customer. But some of these techniques are cross-cutting. You could apply them in other fields even. Something like medical field might be interested in detecting neutrons, for example, or some of the imaging techniques.
Additional questions? So just to mention before I forget, Sara is staying also for tomorrow. So tomorrow she will be up at LBL, and she will give a seminar at 2 p.m. and it will be more on her own research I forgot the title, just for the talk for tomorrow. So it will be from 2 to 3. Location is Building 50 Auditorium up at LBL. So the topic is scintillators for nuclear non-proliferation and nuclear physics studies. So you are all invited to join us tomorrow. So if there are no questions, I would like to thank Sara again.